First of all, some technical issues concerning the final exam for the course. Approximately in a week, maybe about 10th of December or somewhat later, I will send to everybody who wishes to pass exam for this course. Everybody who requests me by email, I will send him problems for home exam, and when you solve them, we meet on Zoom and discuss problems and some theory through the course, and this is the form of the exam. Well, this is technical thing concerning.
Сейчас, прошу прощения, а это еще раз когда? Ну, я пропустил просто. Когда это будет?
Через неделю я начну высылать, может быть, чуть позже. Вот. Но мне надо написать, иначе забуду. Well, another point which is not technical but very essential, that during the week I still haven't succeeded to fill the gap in the proof we discussed last time. Actually, it was a very big surprise for me that this issue appeared last time. Maybe in the next weeks I'll try to ask some specialists, and maybe this was already known, but maybe not. I don't know. At least I would like to say that there is quite another proof of the same results. There are several proofs, and so, for instance, one of them is due to Nikolai Ivanov, and actually initial proof by Harrer also, except for those techniques that I described last time, it incorporates some much harder technique concerning Teichmüller spaces. My attempt was that this harder technique could be avoided by using R complex and its contractibility. Okay, such approach doesn't work, but not it seems not to work, but not because of my part added to this approach, but because of the initial lemma in Harrer's paper. So I will try to clarify this picture during next weeks, but at the moment the situation is the same as a week ago, so I don't know how to fill this problem. And I looked through several others proofs, not through several. I looked through ideas of Ivanov, and it definitely took too long to describe them, so I will not try to give you another proof of the same result, of this result on the homotopy type of the curve complex. So we just skip this proof. In fact, later I will need only connectedness of this complex, and today I will give you short combinatorial proof of the fact that this complex is connected, except for several examples. And this is much easier than the complete theorem about the homotopy type of the curve complex. But before we pass to this short combinatorial proof and of the connectedness, I would like to say you some words about the true approach which allows to understand that the topology of the curve complex. This approach initially appeared in the paper of Hatcher and Thurston, but for another complex. And it was for curve complex, this circle of ideas was used by Nikolai Ivanov in 1980s. And I will not give you the proof today, but I would like to stop for a moment on ideas which allow to get the proof. They are very useful, and I think it's important to understand that ideas of such kind also can be used to study complexes like curve complex. The idea is as follows. Assume that you have a Morse function on your surface. Morse function can be always you can always think of it as a height function for so we always can draw it like that. Okay, the Morse function has finitely many non-degenerate critical points on pairwise different levels. Pairwise difference of levels sometimes usually is not included in the definition of Morse function, but let us consider Morse function with pairwise different values in critical points, though it is not so important, but still. A wonderful idea by Ivanov is that, and to some extent it goes back to Hatcher and Thurston, is that, but for another complex, is that, look, any Morse function produces a simplex in the curve complex. Namely, we can consider all simple closed curves that arise as connected components of the level sets. So, for instance, these I prefer to draw something like that. For instance, this curve that, but look, this curve is also a level set, but it is an essential. If it is an essential, we just skip it. But let us consider all connected components of level sets, or of non-singular level sets. So we just skip all singular level sets and can consider connected components of non-singular, essential connected components of non-singular level sets. And these are pairwise non-intersecting simple closed curves, and so they give a simplex in the curve complex. Okay, and in some sense, in some sense, we obtain a correspondence between Morse functions and curve complex. This is not a map. This is now I'm going to say only words about ideas, but this is something like a map. Given a Morse function, we get not a point in a curve complex, but we get a simplex. Given a point in curve complex, actually, it is not hard to show that we always can realize it by a Morse function, but not by a unique Morse function. But there is correspondence which allows us to pass through functions to points in curve complex and vice versa. And how do these correspondence work? Yes, first of all, a good question. There is one point about we need to be careful here. What is it possible that all level sets, all connected components of all level sets are inessential? If it is possible, then we cannot get a simplex in the curve complex. We just skip all curves. But it is not hard to see that except for certain except for several small genus cases where in fact curve complex doesn't exist. So almost always it is impossible. It is an easy exercise that there are always essential curves in at least a one level set. So among all components in non-singular level sets, always there are essential curves, except for very low genera examples, which are not interesting. But well, now how to get some topological properties of the curve complex from such approach? For instance, how to get connectedness? Look, take a point in curve complex and another point in curve complex, and find here, so this is point A and this is point B, and find here functions, two Morse functions, which give well, they do not give points, but they give some simplices containing these points under this correspondence. Now the next set of ideas is on the side of Morse functions, and this is called Morse surf theory. The idea is to study singularities of functions in families. Namely, if we have just a single smooth function on a surface, then we can always approximate it by a Morse function. But if we have two Morse functions, then we can always connect them by a family of smooth functions, for instance, just usual segment in the space of functions. But it is not true that the functions in the family are Morse again. They can have worse singularities. But we can always approximate here this path in the set of functions, so that only certain rather easy singularities, could I mention one singularities, arise. Singularities only. It is not hard to show that in fact in this particular case, where we approximate one-dimensional family of smooth curves, then we can always achieve that all non-Morse singularities are like that. We sometimes have singularities of the following kind. In certain coordinates, in certain smooth coordinates. Look, this function, ft is a function, xy are local coordinates on our surface, and ft is a smooth function dependent on a parameter t. In this particular case, when this function is as written, it has only Morse singularities, provided that t is not equal to t0. And when t is equal to t0, then this is a function x cubed plus minus y squared, and it has a non-Morse singularity at point 0, 0, but well, this is rather easy. This is the easiest non-Morse singularity. So one of the claims of this Morse surf theory, which is further development of the Morse theory, is that in families, in one-dimensional families, we can always achieve that only Morse singularities and singularities of this particular type exist. And then we can look how, looking on this picture, actually we may ask, is it possible, actually, do we actually need that the function is Morse? Suppose we have a non-Morse function, we still can, but still with finitely many critical points, we still may take connected components of non-singular level sets and again provide a simplex. And if we pass along a family, then this simplex varies continuously. This means that we can pass from a simplex to its face and from face to a bigger simplex, but we cannot jump. So the points are connected by a path in the curve complex. Well, so if we can apply the same argument for non-Morse functions, then we just deduce that any two points are connected. Well, we can get it by free, since there are situations when curve complex is in low genera when it is not connected. And indeed, this is not for free. The only question is again about this word essential. For each type of singularities, we need again ask, is it possible to find a function with prescribed types of singularities so that all connected components of non-singular level sets are inessential? If it is possible, then our argument doesn't work. But it turns out that for this particular type of singularities, this type plus Morse, 3g plus n greater than or equal to 5, is exactly a sufficient condition to understand that under this restriction, any function with such singularities has an essential component of non-singular level set, and so on. Well, I just need to say that we have only one such singularity at any moment of time. It is important. We can avoid that we have several at the same moment.
Сейчас, можно несколько вопросов задать мне?
Да, конечно.
Вот, во-первых, первое соответствие про морсовские функции и curve-комплексы. Там имеется в виду, что мы получим... ниже, вот, еще ниже.
Да?
Да. Вот, и имеется в виду, что мы получим каждую... То есть, что мы каждое получим справа? Мы получим каждый симплекс, только каждый симплекс мы не получим, правильно я понимаю, вот, например?
Каждый симплекс можно получить из некоторой морсовской функции, это легко.
То есть, в частности, можем получить каждую точку отдельно?
Нет, мы не можем получить точку, мы вообще не получаем точки. Ну, просто мы можем получить внутренность любого симплекса, да. Ну, в частности, каждая точка в ней лежит, да.
Не, имею в виду, что точка же тоже симплекс, или имеется в виду, что объединение симплексов, которые мы справа получим?
Нет, симплекс комплекса. В комплексе есть симплексы с вершинами, которые являются... Ну, там есть вершины, там есть симплексы.
Ну, симплекс имеется в виду полной размерности, мы получим справа.
Нет, как любой размер. Сейчас. Наверное, мы получим достаточно большой симплекс. Да, мы получим какой-то симплекс, содержащий А, вот так.
То есть для каждой... То есть утверждение такое, что
точки
можно получить симплекс, содержащий ее.
Угу.
Вот, хорошо. Тогда еще вопрос. Так, тогда теперь ниже. Можно, пожалуйста?
Да.
Мы еще, по идее, должны получать особенность, когда у нас две критические точки на одном уровне, или это...
Да, правильно.
И еще у меня один вопрос будет.
Это правда, их тоже надо добавить. Да, давайте.
Вот и последний тогда. А можно ли аналогичным образом пытаться доказывать связанность? Ну, в смысле, не просто связанность, а там сколько-то связанность, если изучать более сложные особенности?
Можно. Я как раз про это хотел сказать. Yes, and further, in the same way, we can apply the same ideas for further types of singularities, and study two-parametric families, three-parametric families, and think about and understand connectivity of higher connectivity, K connectivity of curve complex from this circle of ideas. And this is the main point, which I would like that there are proofs from this circle of ideas.
Извините, а больше одной морсовской функции, которая, ну вот если я возьму, ну вот если я хочу какую-то точку взять, да, и взять симплекс, который ее содержит, все симплексы, которые ее содержат, да, то эти морсовские функции, которые будут описывать вот эти симплексы, они, ну, будут как-то там, на них будут какие-то соотношения, или это будут самые разные функции?
Много таких функций разные. Нет, это как бы нет необходимости тут. Вот, ну вот, в общем, это я хотел сказать только на идейном уровне, потому что лезть в эту технику как следует, но это надо разбираться вот в этой вот теории Морса-Серфа как бы по-настоящему, и этого мы не будем делать точно. Well, so this is what about this circle of ideas, and now let us give a simple proof, simple combinatorial proof, simple combinatorial proof of connectedness of the curve complex for under this restriction. Oh, sorry, 3g plus n greater than or equal to 5. We already discussed that we have several counterexamples when it is not connected for small g and n. We have discussed them. Well, and actually, this proof is also very useful since it also shows type of combinatorial arguments that often work, but they good. Usually, such combinatorial arguments work good to show connectedness. Sometimes simply connectedness, but in higher situation when we try to understand higher topology of complexes. Usually it is hard to understand anything about combinatorial arguments of such type as I will discuss now. Well, so the idea is look on two vertices of curve complex. I recall that vertices correspond to vertices of curve complex, and vertices correspond to essential simple closed curves. Simple closed curves on our surface alpha and beta, and when we have two essential closed curves, we can ask how bad are they situated with respect to each other? And this is described to some extent by their geometric intersection index. Look, if geometric intersection index is just 0, then the vertices alpha and beta are connected by an edge. So we are done. Then we need to prove connectedness. We need to prove that from any vertex to any other vertex, we can go by a path. But if they are connected by an edge, then of course, that's all. Next situation is suppose that geometric intersection index is 1. This is just next situation. Okay. Let us look on this situation in detail. Well, suppose that then we can achieve by anisotropy that these two curves just have one transversal point of intersection. This means that if we take a regular neighborhood of this union of curves, we get a surface like that. And it is not hard to see that this is a one-punctured torus, a surface of genus 1 with one, not one-punctured, actually. I would prefer to think of it as of surface with boundary component. So this is a torus with one boundary component. Well, now look how this surface is situated in our whole surface as Gn. Well, so I would like to look on this curve gamma, which is the boundary of this of this torus with one boundary component. The gamma is the boundary component. Okay, boundary gamma is a separating simple closed curves. We know that All separated simple closed curves look in the same way if they are just characterized by genera and numbers of punctures on their sides. So gamma up to some homomorphism looks like that. We have here a one punctured torus, and we have here all on the other side, we have all the rest G minus 1 handles, and we have here all n punctures. Look, if on the right hand side of gamma there is at least one handle or at least one puncture, then gamma is essential. Oh, no, sorry, at least one handle or at least two punctures. I recall that a curve going around one puncture is inessential. But if G minus 1 is at least 1 or n is at least 2, then gamma is essential. Under our restriction is 3g plus n greater than or equal to 5. It is easy to check that these conditions are fulfilled. So gamma is essential. Look, then alpha and beta can be connected by a sequence of two edges. So we again prove that they're connected by a path. Now suppose that alpha and beta have intersection index which is greater than or equal to 2. What is sufficient for us? It is sufficient to connect alpha and beta by a sequence. We can start with alpha, which we denote by gamma 1, then go to gamma 2, just not go, but just gamma 3, etc., and some gamma n, which is equal to beta. If we can find a sequence of such kind, so that the geometric intersection index of any two consecutive curves is later than or equal to 1, then we are done. Since we know that if the geometric intersection index of two curves is either 0 or 1, then we can connect them, the corresponding vertices. So if we find such a sequence, then everything is okay. How to find such a sequence? Look on intersection points of alpha and gamma and beta. We have at least two such intersection points, and let us look on this intersection on two intersection points which are consecutive with respect to beta. So we go along beta and we take two consecutive intersection points with alpha. Well, there are two possibilities. Let us orient alpha. Then there are two possibilities. First is that orientations in these two pieces of alpha agree like that. And second is that they are opposite to each other. Well, let us study these cases separately. First of all, first case, alpha. Well, if we have two segments on a simple closed curve, then of course, if we start moving from this segment and go along the orientation, then we arrive to the beginning of the second segment. So there is, it goes in some way, it goes like from here to here. And also it goes from here to there. So the curve is something like that. I mean that in this part, we may intersect beta several times, but alpha is not self-intersecting. There are many intersections with beta here. But okay, many means that it is easy to compute how many of them are. There are totally, if we mark intersections with beta, then except for those two, yes, we mean that alpha and beta are in minimal position, then except for those two, there are exactly E alpha beta minus 2 other intersection points with beta. And now let us consider a new curve. Yes, I draw here some pieces of beta. And now consider a new curve. We start moving along this part of alpha, being on the right of alpha. So we move like here. We arrive here, and then we just go like that. Well, this is a curve gamma. First of all, let us compute its intersection indices with geometric intersection indices with alpha and with beta. First of all, it is easy to see that this gamma has a unique intersection point with alpha. This is, we always go just along alpha, no intersections, and only here we cross alpha once. If we have one intersection point, then the intersection point with alpha, the intersection index is always 1. I just would like to stress that we cannot make it is never 0, that the intersection index modulo 2 is just the number of crossings. Since we have one crossing, we cannot obtain 0. If we had 2 crossings, it would be possible that the intersection index is in fact 0, not 2. But if we have one crossing, then the geometric intersection number is always 1. So, and in particular, it follows that gamma is essential. The matter is all in essential simple closed curves have 0 intersection indices with all other simple closed curves. So, but now let us not compute, but estimate the geometric intersection number of beta with gamma. Look, it intersects all points where all other intersection points with beta give intersection. Here we have intersection points between alpha and beta, and each of them corresponds to a point, to the intersection points of gamma and alpha, and there are not more than, if we compute these points, then there are not more than E of alpha beta minus 2 of them. And we have one more point here. So we have an estimate that this is less than or equal to E alpha beta minus 1. Actually, this estimate can be made much better. The reason for this is that, in fact, we have another possibility to choose gamma. Vice versa, we may go here on the left and then cross like that. All the situation is the same, but now we go around we go around the second path here, and actually any intersection point with beta is computed only once, either for a violet curve or for a pink curve. So choosing between them, we may always assume that not greater than a half of this amount of point yields intersection point with gamma. So choosing one of these 2 points, we may achieve that the estimate is in fact like that we have half of this amount plus 1, and this means that we have but actually this doesn't matter. The most important thing for me is that this is less than for alpha and beta, and so we make the first step from a curve alpha. We pass through to the second curve gamma, which has smaller geometric intersection number with beta, and iterate on this procedure, we get the required sequence. But I considered only one case out of 2. We have another case when we also need to do a similar thing. Namely, we have case like that. In this case, the situation is as follows. So this is alpha and this is alpha. If we go here, we after some time arrive to the beginning of the next segment of alpha, and here we arrive here. On these ways, there are several intersections with beta. Again, except for those 2, there are E of alpha beta minus 2 of them. So let us again consider 2 curves. Here we just go like that. This one is gamma 1, and those one, oh sorry, is gamma 2. Look, here we must be more careful. The matter is that it is possible that one of the curves gamma 1 and gamma 2 is inessential. Let us study the question of whether these curves are essential or inessential. Well, first of all, let us understand that if at least one of the curves is essential, then we are done again. The matter is that these curves are disjoint. Yes, the matter is that these curves are disjoint from alpha. So both these intersection numbers are 0. This is actually the reason why this situation is harder. We cannot use this type of argument that the curve is essential since it has non-trivial intersection number with another curve. Here the numbers are trivial, so we do not know whether gamma 1 and gamma 2 can be essential. It can be inessential. But at least we know the following, that if we compute the total number of intersection points of gamma 1 with beta and of gamma 2 with beta, then we get E of alpha beta minus 2. Maybe by anisotropy it can be decreased, but not increased. But we at least know the following estimate, that the sum of these two intersection numbers is less than or equal of E alpha beta minus 2. So any of these intersection numbers, is strictly less than intersection numbers of alpha and beta. So if at least one of gamma 1 and gamma 2 is essential, then we are done. Now let us, so suppose the converse, suppose that gamma 1 and gamma 2 are both inessential. So suppose both gamma 1 and gamma 2 are inessential. This is the only case we need to handle. Look, first of all, if a curve is inessential, then it is always separating. Any inessential curve is homologically trivial, so it separates the surface. And the curve is inessential if and only if it separates a surface so that one of the parts is either a disk or a one-puncture disk. Look, for gamma 1, we have this part, one of the parts, the part outside. Well, this part of gamma 1. It cannot be a disk or a one-puncture disk. Why? Because this part contains an essential alpha. if it is this part contains the curve alpha. Alpha is essential. If the part was a disk or a one-puncture disk, there are no essential curves inside it. So this is not the case. So we have only the second possibility. Those parts can be either a disk or a one-puncture disk. Yes? But this green part cannot be a disk, only a one-puncture disk. Why? If this was a disk, then we have a bigond here, between alpha and beta. Alpha and beta. I'm sorry, there is some problems with pointer. It doesn't want to go as I show. I don't know why. Do you hear me? Maybe this is...
Да, слышно.
То есть это не с интернетом. Я не знаю, у меня не идет за карандашом. Это самая чуть-чуть какая-то проблема. Вот. Well. This would be a bigond if this green part was a disk without punctures. But we, from the very beginning, we assumed that alpha and beta are in minimal position. So this is not a bigond, but this is not a disk, but is a one puncture disk. Similarly, here the second part the part here is also a one punctured bigond, a one punctured disk. And well, so this is, we see that the situation is indeed possible, but the situation is yes, the situation is actually possible, and we need to take care about it. So let us draw it in more details. We have the following situation. We have beta, and we have alpha is like that, so that there is one puncture here and one puncture here. And these parts are disks. First of all, I claim that in this situation, how can let us study any other intersection of beta with this disk. So look here we have the following situation, that this is a two puncture disks, so alpha is essential, but any half is inessential. So we need to take care of this particular situation. Each half is inessential, and alpha is essential since it encloses two punctures. Let us look how any other intersection between alpha and beta can look like. So is it possible that there are more intersections about alpha and beta? If we had an intersection like that, so, well, any arc in, if we have a two-puncture disk, that then any arc is either like that or like that. It either separates punctures from each other, or it doesn't separate. If we have a situation like that, then we have a bigond here. And so alpha and beta are not in minimal position. So this is impossible. So the only possibility is that we have several arcs of beta going like that. So the only possibility is that beta crosses alpha and crosses this disk several times, like is shown here. Look, now orient beta and orient beta and we may change the roles of alpha and beta. Here, if we have two consecutive lines here which have the same orientation, then we are done again. Since we can interchange alpha and beta and proceed as in the first case. So we are done again. Now the only case which is still to be considered is as follows, that we have several such arcs of beta, and they are their orientations alternate. The orientations of any two. Oh, sorry, my picture is here down and here up. So the orientations of any such part is shown. Okay. Now, well, are there any ideas how to proceed in this case? This is a very particular part. Still, we need to consider this funny case. Well, actually, let us again go by cases. Oh, sorry. Assume that we start moving along this curve. There are two possibilities. First, it is possible that we arrive, oh, sorry, not here, but we arrive we arrive from the other side. Well, say here. Okay, and actually this case is easy. Look, now we started from let us understand what we have done. We started from the case where there are two consecutive points of different orientations, two consecutive points along beta. And we understand that the only bad case is when here and here we have one punctured disks. Yes. So now we started from these 2 points, these 2 red points. But now let us consider another points, this point and this. They are again consecutive points along beta. They again of opposite orientations. But now the same argument shows us that the only bad case is when this part and those part are also one punctured disks. These two must again be one punctured disks. So in all other cases, we again are done. We already considered that. But in this case, we arrive to a surface genus 0 surface with 4 punctures, which doesn't satisfy our. So this situation is possible, but only when we are not in our case. Indeed, on a sphere with 4 punctures, we have these two simple closed curves, this one and that one, which have geometric intersection index 2, and it is impossible to pass from one to another by a sequence of curves with consecutive index and geometric intersection numbers 1. But it turns out that this is the only example, but we still need to consider another case. Another case is like that again, we have alpha here. We have several possible intersections with beta. We have several intersections with beta going in opposite directions, consecutive in opposite directions. And we have 2 punctures here. And but the situation is that when we go here, then we always arrive from the same side. Actually, it still doesn't matter. We again can consider these 2 consecutive intersection points, and we again get that both this part, the only bad case is that both this part and sorry, not these cases. So sorry. Here I'm not precise enough. Let us think. It's not good. Sorry. Кто-нибудь понимает, как это делать? Совсем как-то просто. Everything is the same, of course. Yes, here the bad case is only if this part, and we again need to consider the two corresponding parts. I don't know why I stop here. The only bad situation is that when this part between this arc and that arc, and another part is between this arc and that arc. So this is the part which is exterior with respect to this. When these two parts are one puncture disks, and if this is the case, then we sorry. Меня слышно?
Да, включился только этот доска.
Доска. Что случилось сейчас? Извините. Что-то у меня хулиганит планшет. Так. Oh, well, so again, the only bad case when we cannot apply the same argument is when these two parts are one puncture disks, and again we have four punctured sphere. So the exceptions can exist only in the case of four punctured spheres. In all other cases, we have proved the connectivity, the connectedness. Okay. Next. Well, next, there are many versions of the same arguments. Maybe it was too boring to consider them in details. There are many versions of curve complex. And these versions are very natural. We can consider non-separating curve complex by allowing only non-separating simple closed curves. And again, any non-separating essential simple closed curves, of course. So vertices are non-separating essential simple closed curves, and again, a collection of vertices is span a simplex if and only if the corresponding simple closed curves can be made disjoint by an isotropy. Similarly, one of course can consider separating separating curve complex by allowing only separating curves. Again, separating essential curves. Well, okay. Good exercises are that, again, under certain conditions, except for several exceptions, these complexes are have good properties. Well, so first, so exercises, since it is not so interesting, we need to follow the same line, the same combinatorial argument, and actually we may deduce it from the case of usual curve complexes. But what is true? First of all, that non-separating curve complex is connected whenever G is at least 2. Look, it is not hard to see that it is not connected when G is either 0 or 1. Actually, if the genus is 0, then any essential simple closed curve is separating. There are no non-separating simple closed curves on a sphere. So if G is 0, then the non-separating curve complex is just empty. If G equals 1, then this complex is non-empty. But look, if you have two simple closed non-separating, a curve on a torus is non-separating if and only if, after forgetting about punctures, it is homologically non-trivial. Separating, non-separating if and only if it is homologically non-trivial. But any two curves on a torus which have different homology classes are intersecting. Any simple closed curves with different homology classes are intersecting, so we again have a non-connected complex. The second exercise is in which cases this separating curve complex we can use here S. Oh, sorry. So here I do not remember the exact answer, but it is not hard to understand in which cases this complex is connected. Again, it is always except for several examples. Well, and there is one more interesting version of non-separating curve complex. This is particularly useful for this version is particularly useful for proving for finding a set of generators for the mapping class group. This is so-called modified non-separating curve complex. Actually, this is not a complex. This is a complex. It is one-dimensional complex. So actually, this is only a graph. It is better to say that this is a graph. And the idea is as follows. If we have in usual non-separating curve complex, two vertices are connected by an edge, if and only if, so in usual simple closed curves, non-separating curve complex, two vertices are connected by an edge, if and only if their geometric intersection index is 0, if and only if they can be made disjoint. But in this modified curve complex, which is just here we define only edges. We do not want to even to think about higher dimensional simplices, but we connect two vertices by an edge if and only if their intersection index is exactly 1. This is very convenient since first of all, intersection index 1 means we have discussed that any two pairs of curves of simple closed curves of intersection index 1 can be taken to each other. The mapping class group acts transitively on such pairs, and we see here that these are curves which are on distance 2 in usual, not all pairs, but some pairs on distance 2 in usual non-separated simple closed non-separating curve complex. So we have this version, and again exercise 3, that this guy is always also connected whenever G is at least 2. Well, oh, sorry, this one is even connected whenever G is equal to greater than equal to 1, and it is better than 2. Okay, now it's time to make a break. Let us have a 10-minute break, and then we proceed.
А можно вопрос напоследок?
Да, конечно.
Вот последний комплекс, ну, последний граф, я правильно понимаю, что нужно выкинуть всякие, как называется, ну, кривые, которые, например, если край проходит вокруг двух точек, выколотых в остальном гомологически?
Мы их уже выкинули, они все разделяющие.
Ага, все, спасибо, да.
Так что да, их нужно выкинуть, но мы это уже сделали. We see that there are many useful complexes for which simplices and vertices and simplices are indexed by either simple closed curves or multi-curves or some object like that. When the main idea behind why these complexes are useful is that mapping class group acts on every such complex, and we may study group properties from this action. And when a group acts on a set and we are interested to understand the group, the two questions, the two things are important. First of all, to understand the topology of our space on which the group acts, and we have already done some things about it. And second, to understand the stabilizers of vertices and of cells of our complex. And so we are constantly interested in such things as stabilizers of multi-curves in mapping class groups. And now, today, the second part of the lecture will concern several very useful exact sequences that allow to understand such stabilizers. Well, let us start from a rather simple case just to begin, but it is already very important. Let us consider a non-separated. Yes, our surface can have now punctures or boundary components or both. It is not so important. The results here are rather general. Suppose that we consider a non-separated simple closed curve. But let us try to be careful about the following. The mapping class group does not act on curves. A mapping class doesn't act on curves. It acts only on isotopy classes of curves. So let us distinguish between alpha and isotopy class of alpha, and this isotopy class is A. Oh, and we are interested, mapping class group of the surface S acts on the set of isotopy classes of simple closed curves. And we are interested on the stabilizer of the isotopy class A with respect to this action. Actually, there are two possibilities to understand, and not even two possibilities to define this stabilizer. There are two different actions and two different ways to define the stabilizer. They are rather similar to each other, and they can be easily connected to each other, related to each other, but they're different. Namely, look, it is possible that some orientation preserving, we deal only with orientation preserving homeomorphisms here. But it is possible that an orientation preserving homeomorphism takes the curve alpha to itself, reversing its orientation. For instance, an example of such homeomorphism is like that. We can consider this handle and take a half twist along this pink separating curve. So we rotate this handle by half of the full rotation by pi, and then glue again. And not glue again. We just let's think that we do not cut. We just rotated. This surface is made of some elastic material, and we just rotate the handle by pi. So such half twist takes alpha to the same curve but reversing its orientation. Or for instance, just hyperelliptic involution takes alpha to itself, reversing its orientation, even easier example. So we may consider A as isotopy class of non-oriented curve, or as an isotopy class of oriented curves. And the stabilizer will be different. But this difference is by index 2 subgroup. So of course, if we consider usual notation, and this is a rather convenient notation, is that we consider, we denote by A stabilizer of A with this arrow, the stabilizer of A as of isotopy class of oriented curves. And without arrow, we mean non-oriented. And of course, there is just an exact sequence like that. So this is a subgroup of index 2. And so it is more or less, we can study one of them and we understand a lot about another. And also there are several variants when we have punctures. We can consider mapping class group or pure mapping class group, and even some variants. Let us look on this in details. First of all, so now I will proceed as follows. I will write several exact sequences and explain intuitively why this is true, and just in several words. And after I write several sequences of different nature, I will prove them all. But I don't want to give proof from the very beginning. So first of all, let us assume that our surface has no punctures. So it may have boundary component, but it doesn't have a puncture. Yes. Actually, from now, I would like to consider we, instead of oriented simple closed curve, or instead of non-separating simple closed curve, we may consider separating simple closed curve. What is happening then? Again, we have two possibilities, this one and those one, but it may happen that either we have here Z over 2Z, or we have here trivial group. For instance, for this particular separating simple closed curve, no mapping class can take it to itself, reversing the orientation. The matter is that surfaces on the side, on the right of this curve and on the left of this curve are not homeomorphic to each other. But if they are homeomorphic, then again we get this Z over 2Z. So we have these two possibilities, and I will mostly write sequences about this group, and the whole stabilizer is sometimes twice as big. Okay. So suppose that we have a curve alpha, and its isotopy class A. It doesn't matter oriented or non-oriented, but we always assume that it is essential, of course. So we are interested in stabilizer of the curve alpha in the mapping class group as our oriented curve. But the stabilizer of the isotopy class of alpha. The first claim and is that this is as follows. We can consider a subgroup generated, so we have this curve alpha, and we can consider a subgroup generated by the then twist about this particular alpha. We know that since alpha is essential, this one is isomorphic to Z. And the claim is that we have the following exact sequence. Look, if you have a mapping class that stabilizes A and respects its orientation, then we always, by Alexander's method, we always can represent this mapping class by a homeomorphism that stabilizes alpha pointwise. And then this homeomorphism, we can restrict it to the to the complement of alpha, and so we get a mapping class of this group. This surface is homeomorphic to genus G-1 surface with the same number of boundary components and with 2 punctures. Oh, sorry, but the sequence is written incorrectly. I'm sorry. Here we need to consider pure mapping class group. We always get a mapping class that does not permute, doesn't swap punctures. But if we consider stabilizer of alpha as of non-oriented curve, we get here usual. Note that if alpha is separated, then this surface is not connected. So, but still, mapping classes can be considered. If we consider pure mapping classes that stabilize every puncture, then the pure mapping class group of a disconnected surface is just the direct product of the mapping class groups of the connected components. But if we consider not pure mapping classes, then it is possible that there exist mapping classes that permute the connected component of the surface. Okay. Well, in these sequences, what is obvious and what is not? First of all, it is obvious that the mapping class along alpha stabilizers is its isotopy class. Indeed, alpha is can be replaced by a curve disjoint from it by, and then mapping class along alpha just doesn't affect that curve. So this one is easy. It is not so obvious that this mapping, this Dent twist is exactly the whole, generates the whole stabilizer, and we will prove this. In fact, it is not even so obvious that this homeomorphism is well defined. The matter is that, well, how we define it? We say that any mapping class that stabilizes A can be represented by a homeomorphism that stabilizes alpha pointwise, and then we restrict. But it can be represented by different homeomorphisms that stabilize alpha pointwise, and from the very beginning, it is not so clear why we get to the same homeomorphism, to the same mapping class here. So we will again prove this. More or less obvious, what is more or less obvious is that this is a surjection. Indeed, if we have a mapping class of the surface which stabilize every puncture, then it can be deformed slightly so that it is just it is just pointwise trivial in the neighborhood of every of these two punctures, and then we easily get the corresponding mapping class of the surface. These neighborhoods of the punctures are in the initial surfaces, they are neighborhoods of alpha. So if we get a homeomorphism which is trivial in neighborhoods of punctures, then here we get a homeomorphism which is trivial in the neighborhood of alpha, and then of course it lies in the stabilizer. So it is trivial that this is a surjection, but it is not so trivial that this is a well-defined homeomorphism. Homomorphism, sorry. Well, and now let us also say what happens if we already have punctures. If we already have punctures, well, there is an easy case when we take stabilizer. Now we allow punctures. In pure mapping class group, this is an easy case, and of R with as oriented curve. Then this is an easy case, and we get the same claim. But if we consider not the group, not pure group, if we allow to be mute punctures, then the formulation is not so easy, namely, or if we allow A to consider A as of an unoriented curve, namely, the situation is the following: that if we have stabilizer in mapping class group of the surface of A, then we get the mapping class group. The question is, what is here? Here is the mapping class group of S without alpha, but look, this surface is surface of genus G with B boundary components and with n+2 punctures. And two punctures are special. They correspond to these two special punctures. Let them be P1 and P2. These are two special punctures that correspond to two sides of A, of alpha. And other end punctures existed before. So here we have mapping class group, which stabilizes every of these two punctures.
Why is that genus is G?
Well, oh, sorry, genus is not G. Genus is not important here. It may be even not connected. I just want to say that there are some problems with punctures, that if we study stabilizer in mapping class group that allows to permute punctures, then we do not get here the mapping class group which allows to permute all punctures. It allows to permute punctures according to some rules, and in this case we have the sequence like that. But another version is that if we get here this group as an unoriented curve, then we need to consider those mapping class groups that preserve these two punctures together. So it is allowed to swap them, but it is not allowed to swap between them and other punctures, and so on. And also instead of one curve, we may consider a multi-curve. That is a union of all curves, and then we have a similar sequence. Multi-curve, we mean that all components are essential and any two components are not homotopic to each other. Then we have the following. We have subgroup generated by these den twists, and we already know that it is just free abelian group generated by these den twists. Then it goes to stabilizers of pure, again I write in pure mapping class group of M respecting. Now this arrow means that we respect orientations, and besides do not swap components. Now we have one more degree of freedom. We may allow to swap between components of M, or we may consider stabilizer which is which stabilizes every component personally. So in this, the most restricted way, when we stabilize every component personally and preserve the orientation, we get exactly to the pure mapping class group of S without M. In all other cases, similar sequences exist. So we may consider different, we may consider not pure group here. We may consider different ways to stabilize M here. And there are similar sequences, and I will write here we always have more mapping class group of S without M with certain rules of permuting the punctures. And in each case, these rules can be easily understood. which rules should be introduced to understand the corresponding stabilizer. So there is some zoo of surfaces of sequences of such kind, and they are useful since they allow to reduce the question on stabilizers to the question on mapping class group or pure mapping class groups themselves. And sequences of such kinds are called Biermann, Lubotsky, McCarthy exact sequences, or they are also called the Cotton exact sequences. Okay, applying these Cotton exact sequences, we arrive to, from stabilizers, we arrive to mapping class groups, but we arrive to mapping class groups of a surface with punctures, even if we started from a closed surface. Even if we originally are interested in a closed surface, we need to introduce punctures here. On the right, we always have surface with punctures. So the next type of exact sequences concerns the question of forgetting a puncture and things like that. Look, we have three possibilities. We may have a puncture, we may have a boundary component, or we may have neither puncture or no a boundary component. So there are three possibilities. First of all, we can consider operation of forgetting a puncture. This means that we, from a surface of genus G with n punctures and b boundary components, we would like to pass to a surface of genus G with n-1 punctures and b boundary components. Of course, this is not well defined on the level of whole mapping class groups, since, well, if we want to forget about one puncture and this puncture can be swapped with any other puncture, then it is not a good operation. So this is good on the level of pure mapping class groups. And again, we have variants that say we can forget about two punctures simultaneously if we consider the mapping class group when they are not swapped, or we may forget actually instead of pure mapping class group, we can consider only the mapping class group that fixes one puncture, and other punctures are allowed to permute. Okay, but anyway, we have this possibility to pass from surface of G, to decrease the number of punctures by one. Yes, and of course, on the level of pure mapping class groups, we just have a homomorphism. The matter is that, well, if we have any mapping class can be represented by a homomorphism, and we just may forget about this puncture, and we get a homomorphism of this surface. Okay. Now, suppose that we have not a puncture, but a boundary component. And if we have a boundary component, then there are two possibilities for us. First of all, we may replace a boundary component with a puncture. Component with a puncture. There are two ways to do this. Let beta be this boundary component. Look, first possibility is that this is surface S, we just delete beta, remove beta. And so we get a surface which is homeomorphic to a surface with one. So if this was S, G, and B, then we get S, G, and plus 1, B minus 1. And the second possibility is that we take S and along beta, we attach a one puncture disk. These two operations are, of course, equivalent to each other. We can topologically we obtain the same thing, but I would like to stress that this one is good and that one is bad. Why? Here we have a morphism. Here the surface S is contained in the surface S prime, which we obtained after such attachment. So in this case, we can just homomorphism can be extended by the identity to the whole surface S prime. Isotopies between homeomorphisms are extended by the identity, and so we immediately see the homomorphism from the mapping class group of the initial surface to the mapping class group of this new surface. And let us even be more precise. We again have, we could have another punctures here. It is possible that there are another punctures here, but here we get mapping classes that maybe they permute punctures, but at least they stabilize the puncture P0, and we get this homomorphism. If we use this way of thinking about replacing a boundary component with a puncture, then it is much less convenient to understand how to understand this homomorphism, since here we do not see a good morphism from S to S without beta. So this second type is preferable. This operation of adding disk with a puncture to the boundary component is called a capping. And here we get the so-called the capping exact sequence. And it is like that. Oh, well, this one is the capping homomorphism, and here Yes. The only thing, and this is again Z, the only thing I would like to say that I would like not to consider some very specific small examples. I assume that beta is essential. There are some bad examples. For instance, when S itself is actually, there are two such examples: when S itself is a disk or a disk with puncture, when the boundary component is inessential. These examples are completely not interesting, and I assume that we are not in them. In all other cases, we have this cap in exact seconds. We have here Z, and again, what is obvious and what is not obvious here? The existence of homomorphism is obvious. The fact that T beta lies in this mapping class, lies in the kernel, is obvious, since look, this T beta after the capping homomorphism, it becomes the then twist about a curve around the puncture, and this is a trivial element of the mapping class group. So it is trivial that the composition of this homomorphism is zero. We will prove it is not trivial that T beta exactly generates the kernel, and it may seem that it is more or less trivial that this is surjective. In fact, it is not trivial at all, but we have not proved facts like that. And here we again have, we already have skipped facts like that. Look, in fact, even several minutes ago, I have already mentioned fact like that, and you believed me. Here, when we made a homomorphism trivial in a neighborhood of puncture. Here, the same situation. Yes, if we have, this is just a local question, so we may assume that we are in some neighborhood of origin in R2. So if we have a homomorphism of a neighborhood of origin here to a neighborhood of origin in R2. So if some curve around origin, some circle, look on it, it goes to some nasty circle about around an origin. And actually, if we would like the claim which we constantly use is that up to isotopy, it is isotopic, and with isotopy supported on some compact neighborhood of zero, that it is isotopic to the homomorphism which is identity on on a neighborhood of this point. First of all, let us understand that the usual Alexander's trick doesn't work here. Alexander's trick is for the case when the homomorphism is the identity on certain, maybe large circle. Then, of course, we can easily make its identity inside. But what is, now we consider the case when the image of every circle around the origin is nasty here. some nasty soup. Well, so Alexander's trick doesn't help. Actually, this is not an easy question, and actually, I would say that this is a strong form of the Jordan theorem. Classical Jordan theorem says that for each simple closed curve is up to a homeomorphism as a usual circle. It divides the sphere into parts, and the whole picture is homeomorphic to the sphere with the equator. Strong version of the Jordan theorem is that the same is true not only up to homeomorphism, but up to isotopy. Any such picture is isotopic. And since I haven't proved the Jordan theorem itself, it has no sense to try to prove this improved version of it, and it will take many times. So it is maybe exercise with many stars if you are interested in questions like Jordan theorem to understand why this is actually true. But I will skip this point. So this is true, and there are some technical, it requires some technique to understand it properly. Okay, so this is about surjectivity of this Kaplan homeomorphism. Yes, once we achieve that the homeomorphism is trivial on some neighborhood, then okay, we are exactly in this group. So this is just implies the surjection. Okay, this is, well, so this is the second. First possibility is to forget a puncture. Second possibility is to cap the boundary components. And in fact, we can take the composition of these two. Having a boundary component, we can replace it with a puncture, we can cap it, or we just can glue this boundary component by a disk. We can attach disk without a puncture. This is the third operation that we can consider. This operation allows us to go from surface of genus G with B boundary components and punctures, just we decrease the number of boundary components by 1. And this is the combination of first two, the combination of the operation of forgetting a puncture and of the capping operation. We can just cap the boundary component and then forget about this puncture. Well, I say some words about the capping exact sequence, and we will prove it soon. Maybe not soon. I feel that maybe I'm not sure that I will have time to prove everything that I wanted to do, but at least we will prove this. But I said nothing about the forgetting a puncture. In fact, in the case of forgetting a puncture, we have a deeper situation. It is not so easy. And this is the so-called Biermann exact sequence. There are many works of Joan Biermann concerning mapping class groups. So there are many things named after her. So we already mentioned this Biermann-Lubotsky-McCarthy exact sequence. This is another exact sequence, Biermann exact sequence. And it relates this exact sequence is like that. Well, look on the surface, and the surface may have several boundary components, may have handles, and may have punctures. And assume that one of the punctures is one of the punctures is special, and we consider mapping classes that preserve this particular puncture. And actually, in this situation, it is more convenient to think like that all others are punctures. But this one is not a puncture, but is a marked point. This changes nothing. If we consider punctures or we consider marked points, these are two languages for the same thing. But to distinguish it from other punctures, it is more convenient to do like that. And not only to distinguish, actually, this is now let us look. So let S be the surface. So this Fs is homeomorphic to the surface. Here we have n punctures. X is n plus first. But topologically, S is a surface with n punctures. We do not delete at the point X. The point X exists in S. Other punctures do not exist in S. And this is actually important for the Biermann exact sequence. Since in this exact sequence, there is the fundamental group of S with base X. The fundamental group is maybe the only thing which distinguishes punctures from marked points. If we consider the fundamental group, it is important whether it is a puncture or a marked point. And we need to be in exactly this situation. All others are punctures, and this one is a marked point. And actually, we use this marked point as the base point for the fundamental group. Now, the sequence is like that. Here we have the mapping class group of S that preserves with all mapping classes and all isotopies preserving X. Yes, and here we have the mapping class group of S when we forget about the marked point X. So we have such exact sequence. The construction of this homomorphism is trivial. Just we forget about the puncture X. The construction of this homomorphism is more complicated, and actually this is the essential part. This is called the push map. Pushing along the along a loop. So if we consider a loop representing the homotopy class in pi1, then we can push the point X along this loop. And actually, this is indeed made as follows, that, okay, this is our surface with points, and this is X. And let us draw a loop. Which represents an element of pi1. Well, with base point s x. So we would like to travel along gamma. Look, locally, assume that you have a disk. So sorry, I don't want to dash it. We have a disk, and we have a small part, a small topological segment inside this disk. And we have point X, and we would like to move it to this point. Then it is not hard to this point Y. It is not hard to find a sequence of, this is D2, a sequence of homeomorphisms of D2 to itself. These are homeomorphisms such that they are trivial on the boundary. We start from the identity homeomorphism, and phi t of x of this particular point is the required path. Well, it is a good and easy exercise to construct explicitly some example of such sequence of homeomorphism. Intuitively, we just take this disk of some elastic material and we move x from along the path and look how the disk defaults. Any deformation is allowed, is good for us. So look, we may step by step, we may push this x along the curve. We may decompose the curve. The curve gamma can be self-intersecting, can be very complicated, but we can decompose it into small pieces, each of which is non-self-intersecting, and each of these pieces lies in certain disk, in the interior of certain disk. And we may, in the interior of this disk, we may introduce this sequence of homeomorphisms, and we may extend this homeomorphism to all these homeomorphisms to the identity, by the identity to the whole. So extend by the identity to the whole surface. And then we get a continuous family of homeomorphisms, which starts from the identity, and at the beginning, the last homeomorphism takes x to this point y, y1. Now we can introduce another set of homeomorphism in the next disk, which finally takes gamma 1 to gamma 2. The composition with the original one, not the composition, but we take, to be honest, if we have phi t here, I always mean that phi t is extended by the identity. This is phi t first. If we have phi t second, then we just make the following. We decompose the segment for the time into pieces. Here we realize phi t1. On the next one, we take the composition of the last homeomorphism in the first family, and phi t second. Then here we have phi t third composition with the last of the second and the last of the first, and so on. So we push step by step the point x along this curve, And finally, in several steps, we arrive again to X. What we get? We get a homomorphism of the surface S to itself. And it takes the point X to itself. Since the point travels and arrives to X again. So the last homomorphism, or the last homomorphism, finally we take the homomorphism at t equals 1. Finally we have this homomorphism. And we get into this group, and moreover we get into the kernel of this map. The matter is that if we forget about X, if we allow our isotopy to change X, then we have constructed our homeomorphism together with its isotopy to the identity. So it becomes isotopic to the identity if we allow to change X. But if we require that X is preserved during the isotopy, then we cannot move this X. Then there is no reason why this homeomorphism is isotopic to the identity. And actually, John Biermann proved that this is the obtained exact surface. Sorry, here I forget a very important thing, which is always important in results like that. Theorem by Birman is that this is true, but only if the Euler characteristic of the surface S is negative. Then we have this exact sequence, and it is not hard to see that in cases when the Euler characteristic is non-negative, it is not true. For instance, we have already discussed that for the torus with puncture, or for a torus without puncture, both mapping class groups class group of genus 1 surface, which is just torus without puncture, or mapping class group of genus 1 surface with one puncture, they both are isomorphic to each other and to the group SL2Z. So in this, if S is a torus, then in this sequence, this is an isomorphism. However, we have an non-trivial fundamental group. The group of the torus is, of course, not non-trivial. So the claim is not true. So the claim is true only for negative Euler characteristic. Well, so what is, again, we will prove somewhat later, but what is important here, that these Biermann, Lubotsky, McCarthy exact sequences are very useful together with Biermann exact sequence. The matter is that Biermann, the most convenient mapping class groups are for closed surfaces or for surfaces with one puncture. There are two convenient cases. All other are less convenient. And usually we are interested, and also usually we are interested in mapping class groups, or either of closed surface, or with a surface with one puncture, or with of a surface with one boundary component. So look, Biermann-Lubotsky-McCarthy theorem allows us to pass from a stabilizer to the mapping class group, but to the mapping class group with punctures, with more than one punctures. The number of punctures increases. And now we need to reduce the number of punctures. And this is exactly what the Birman exact sequence does. It allows to decrease the number of punctures, to understand the group with several punctures if we know the group with smaller number of punctures. Of course, we need to be careful about how the punctures are allowed to be viewed and so on, but still it is convenient. Well, and yes, and maybe now it is convenient to join together the Kaplan exact sequence and the Birman exact sequence. So if we have the boundary component, we may be interested in what will happen if we attach a disk with just usual disk without puncture to this boundary component. We may do it in two steps. We may first cap this boundary component, add the disk with a puncture, and then forget about the puncture. So let us look on these two operations in somewhat more details. So assume that we have a surface of negative Euler characteristic, and we are looking on the boundary component beta. Maybe there are other boundary components, punctures, and so on. Then, first, when we cap this boundary component, then this is, let us again think of this point as of marked points. All these are punctures, and that one is marked. So the surface which we obtain is topologically, if we think of this as of marked point x, then topologically it is a surface with one less boundary component with the same number of punctures. But in fact, there is one more puncture which we just I will write plus one marked point. Just we think of it as of marked point. Okay. Now we have these two sequences. First of all, we have Kaplan sequence. Here we have the mapping class groups of the initial surface, and here we have mapping class group of the surface S prime, which fixes this point X. And now we have this Biermann exact sequence. Joining these two sequences together, well, look, we think of this. This one is well, sorry. now we would like to write this Birman exact sequence for the surface S prime. So we just change notation, since this is for the surface S prime. Okay. The idea is that this one is more or less what we usually know. This is we would like to relate these two. So we would like to eliminate this intermediate mapping class group of S prime with X. But okay, just usual algebraic fact that once we have such two short exact sequences, then of course we have first of all we have the composite homomorphism. We can take the composition of these homomorphisms, let us denote it by eta, and then look, what can we say about the kernel of eta? The kernel of eta, this guy, lies in the kernel of eta. It lies in the kernel of this one, and hence in the kernel of eta. And moreover, just the algebraic fact is that these two sequences, short exact sequences, easily imply that there exists the following exact sequence. That the group generated by T beta, the kernel of this homomorphism, is injected into the kernel of eta, and now it is subjected to this one. Well, and moreover, this spectral sequence is the central extension, is a central extension. Which means that this T beta lies in the center of the kernel eta. Well, actually, T beta lies in the center of the whole mapping class group. T beta commutes with all mapping classes of the surface S. So it is a trivial fact that it is a central extension. Well, but a rather easy but important observation is that this kernel of beta has a good topological sense, namely, yes, and this one is Z, just is Z. Namely, there is one situation when we have the same sequence. We can consider a surface, and this surface S has tangent bundle with, this is a vector bundle, two-dimensional oriented vector bundle. Let us consider a sub-bundle consisting of the unit vectors. We can introduce some Riemannian metric in the bundle, and this is a sub-bundle, S1 sub-bundle, unit vectors. Then look, topologically, this is bundle with fiber S1 over two-dimensional manifold. So this UTS is a three-dimensional manifold. If the surface was closed, then this is a compact closed three-dimensional manifold. If the surface was with boundary, then this three-dimensional manifold is also with boundary. If the surface was with punctures, that is incompact, then of course this one is also incompact, but still in any case this is a three-dimensional manifold. And okay, and well, yes, and of course we can write down homotopy exact sequence for this fiber bundle, and it is not hard to see that as a result we get the following short exact sequence. Well, if we have here some base point x, then we have a circle over this x. Let us choose base point upstairs above x, any point above x. Then we get such sequence. And claim is that these two sequences are isomorphic. Not only groups are isomorphic, but this whole sequences. So in fact, we have a natural way to identify the kernel of eta with this pi1 of this three-dimensional manifold. And as a result, altogether, we get the following variant. It is also called Biermann exact sequence. And this is as follows, that we have surface with boundary component, surface of negative Euler characteristic, and we add here a disk, and S prime is S with disk, and then but here is S prime. So sorry. Yes. Sorry, here is also S prime. I forget primes here. I am sorry. No, well, here this is all this is for the surface prime. So oh, sorry. Here we have mapping class group, and it goes to mapping class group of S prime. So this sequence connects the mapping class group if S is, and Euler characteristic of S prime is of course negative. Well, yes. So S is SGNB, and then S prime is SGNB minus 1. Yes, we need the Euler characteristic of S prime. Well, and intuitively this can be thought of, well, this is again a push map here we pushed a point, but if instead of a point we have here a disk, then we can push this disk and simultaneously rotate it arbitrarily. And this rotation corresponds to rotation of, we can choose here one prescribed vector, and this vector will rotate. So we will get, we can realize not only a loop in S, but we can realize any loop in this manifold. Well, so sorry, what is here? Here as well. Yes, maybe that's all for now. I think it's time to stop for today.